So the video is a video of a mouse, and Yankee basically has an inkjet printer upon which he, from below, prints odor trails. So, so that is, and then the mouse he puts on top of the thing, and the question, and then he puts electrodes in the brain of the mouse, and the question is, and he also takes video, and the question is to watch, to try to figure out what the mouse is doing when it's sniffing the odor trail. And so this is the mouse. You see, and Venki is, and then you have to watch. But I just watch the nose, watch what the mouse is doing. It's sniffing along the ground, and then every once in a while it picks his nose up, and he does something else. And this is just the first step of the problem of smell. It's the one that we're most familiar with, namely sniffing. So actually, as it happened, in any research, we sort of started with this movie thinking, well, maybe we could do something to help Venki. Because actually, even the processing, as opposed to like experiments you can imagine doing on the eye with light, the processing of this is hard because it's very nice. The odor trail is down here. The conveyor belt is moving. There's wind in the room, and the mouse is moving its head. And you have to basically, if you really want to do this experiment, you have to be able to say what is the odor that is actually entering the nose of the poor mouse. And in itself, that's a difficult calculation. And actually, we sort of set out to do engineering help for our friend Venki and to simply calculate for him the as a function of time what was happening so that we could try to do decision strategies. But as often happens, research programs destabilize and we started doing something else. So so this is David. Was a postdoc at Harvard up until literally right now. This is his last week at Harvard. He's going to the Max Planck Institute in Göttingen. And he really is the one that carried this forward. We've been helped in what I'm going to tell you. We sort of random walked through various people who helped us. We've been helped not only Venki, who got us started. Dan Lieberman is a human and evolutionary biologist at Harvard who's interested in the evolution of the human head. And he got us very interested in the evolution of essentially the shape of the nasal cavity, which will form the bulk of this talk. And then towards the end, I'll flash something quickly that we've been doing recently, which is that we met through Dan a nasal surgeon at Mass Eye and Ear who basically picks people's noses when they're broken. And she sort of explained to us that actually it was very difficult to measure the flow within the nose. And so we sort of launched on a program to try to help her, and I'll tell you that as well. Anyway, this is just not straight. So olfaction is sort of poorly understood. So there's the dynamics of sniffing that I already showed you, right, which I think is an interesting problem. That is, how should you sniff, and how fast should you sniff, et cetera, et cetera. Because it's sort of active sensing, right? What is the nature of the active sensing that you can undergo to basically affect how you smell? So then there's sort of flow through the nasal cavity, because of course once you get it in there, something happens in there. And then there's the question of how smells are detected and how odors are recognized. And so if you look, this is a sort of lousy schematic of the human nasal cavity. And I'm going to show you more detailed pictures as we go along, but roughly speaking, what happens is that there are odor molecules outside the nose. You sniff them in. There's some sort of a flow in here. The nature of the flow we will discuss. Then the entire nasal cavity, which has a very complicated morphology that I will show you in a couple of minutes, is covered with mucus, and then the mucus actually is covering the olfactory receptors, which are actually receptors that bind small molecules. Now, and so that's the sort of baseline thing. Now, the computational challenge here is severe. It turns out that humans have somewhere around 300 different olfactory receptors. These are receptors these are proteins which are different than each other and bind and have different binding pockets. We, of course, are able to detect more than 300 small molecules. So a natural question is, how does that work? And there's a sort of long story that we worked some on that I might tell you a little bit in this talk, depending on how this goes, on the sort of combinatorial coding with respect to this. So there's a part of this problem which is how you go off of the, right? How does the signal go into the brain and actually detect this? There's this sort of detection pathway. Just to get you more into, but I'm going to focus mainly here on the physics of this. So one thing which I guess I find sort of fascinating is the following. So odor molecules are volatile. So if you're cooking, if you're cooking, the flavor molecules boil off, right? Which means that they're more volatile. So things that boil off tend to be less soluble in water. That's just the way life is. And one funny thing is that You can talk, as we will, about the concentration of molecules within this nasal cavity, which is air, but eventually these things have to dissolve back into mucus, which is essentially water, and the solubility of the volatiles in water is actually, is not that high. And actually the body has, or biology has invented sort of a remarkable solution to this, just to sort of illustrate the complexity of this problem, which is that there are proteins that are dissolved in the mucus that are called odorant binding factors. And there are many of them. And the odorant binding factors are essentially there, it seems, to increase the solubility, to increase the effective solubility of the volatile odor molecules and to deliver them to the receptors. And so there's a sort of another processing step that basically occurs between there and there. Now, fortunately for the fluid mechanics, which will form the bulk of this talk, we don't have to worry about any of this. This is just the boundary condition at the edge of our cavity, which will absorb the molecules. Sorry, I haven't had enough coffee today. So the receptors are on cilia. I've already driven that. So actually, it turns out that the distribution of receptors is non-uniform. This is a picture. Actually, let me just show you this. Sorry. So this is a picture from Linda Buck, who was one of the people who discovered the odor receptors. And this is a cross section of the human nasal cavity, which is sort of remarkably complicated. And the yellow, she's labeled the odor binding receptors. And you'll see that they really cover the entire thing, although the spatial distribution of different types of receptors is non-uniform. And one of the sort of things that's sort of gone through this field for some time is whether or not there could be some sort of a spatial code with how you do odor. For example, and this is complete nonsense. You guys are recording this, actually. I have to be careful. It's like, the problem. It says on air at least, so you can be reminded that you're
We're recording these comments also.
I understand that. It's creepy. This air recording. Okay. Right. You could imagine that, like, the nose, maybe it's like a mass spec. You blow it in, and at different positions, you deposit the different volatiles at different positions, and then you do the processing that way. At some point, we actually were, we chased this idea down. We had some way, which I'll tell you later, to compute flows in actual noses, and but it's sort of nonsense. There are lots of nice ideas.
How should I see this picture?
I'm going to show you. I'm going to explain the geometry. This is a cross section. This way. These are the two. We have two noses. Actually, we don't even know. If you go and ask why we have two noses.
Everything's symmetric.
Not everything is symmetric. Your heart is not symmetric. Your liver is not symmetric.
Most things.
Okay.
All things are symmetric.
So this talk, there are lots of questions. This talk has sort of two parts, but there is really only one part, because I'm not going to talk about this. These are the two projects that David worked on while he was a postdoc, or two of the projects that David worked on while he was a postdoc. So I'm going to, and this is in the sort of spirit of Darcy Thompson, and I must say I have a love-hate relationship with optimal design principles. I, for the most part, hate them. On the other hand, like everyone else, I can't seem to stop constructing them. It's really sort of unfortunate, but in any case, so I'm going to just simply ask the engineering question of, how should you design the cavity to best uptake odors, et cetera, and that's basically what most of this talk is going to be. So it's ignoring the receptors and how they work and things like that. Although I hope if nothing else I've sort of motivated you that there are really lots of questions here. And although there are things that are understood, it's not that this is there's a lot that we don't know about this. So okay, so actually that's a lemur. That's going to be this one. I can't use PowerPoint either. So so this is a side view of the human nose, and there are sort of two routes that air gets into the human nose. One is what people call orthonasal, and the other is retronasal. Retronasal is the fact that there's a hole in the back of our mouth, or whatever you call it, which basically when you eat, the volatiles are released to go upwards this way to hit the nose, which is one of the reasons that humans have such or in fact is the reason that humans have such a refined sense of taste, because it can go both ways. Now the just general gross morphology of the nasal cavity changes across organisms. So this is a lemur. So this is a lemur, which also has retronasal flow, but you just see that the entire morphology looks different. And I mean, one of the sort of curious things about this business is that, I mean, at least there's anecdotal stories which are even true that, dogs are better at smelling than we are, right? And so, you sort of have to ask, I mean, an example of a question is, well, why, right? And there are sort of two possible classes of answers, getting back to my original slide. One class of answers is that, well, it has something to do with the sort of the way that the receptors, the number of protein receptor processing part of this, that is it. But the other part is that there could be something having to do with the way that the system is designed, the fluid mechanical part of the system is designed. And I think that this is accurate, that it's not, I mean, nobody really knows the answer to this. Okay, so now the nasal geometry is complex. So this is a CT scan of a human nasal cavity. Actually, this is what people call the standard nose within humans. This comes from.
Can we stop it at one stage and have a look?
Oh no, I don't. On my screen I can. Oh, that stopped.
Are those bulbous structures hollow?
No. So the dark part is where the air goes through. So the hollow part is the dark part. So this is inverted. This is the thing. So I'm gonna now make it go, sorry.
So you mean what is filled is actually
Yeah.
empty first?
Yeah, what's filled is empty, sorry.
Oh.
Just to make it,
I
well,
see.
So this is the air, basically.
yeah, this is where the air is. This is the shape of the cavity, sorry. This is I can't make this work. Here, I'm gonna try to go out of this. Maybe I can make it work this way. Does that work? Okay, well, sorry, I'm really bad at this.
Oh, that's good.
So there, you can see, and so the air goes in, and you see as you go in, and I'm gonna start showing you cross sections laterally, right? There's a pressure gradient, remember, that goes from the back to the front. So you're sniffing inwards, and this thing, there's all this stuff, there are the sinuses, right? There's sort of side cavities and stuff off the side, but just the morphology of basically the tube when you go that way is remarkably complicated. It's not great how it spins. Okay, so this is a side view of it. This goes from the nostrils to the throat. So the pressure gradient is across this way. And now what I'm going to do, just to help you with this, is to make 2D slices. Okay, so this is a pipe. This is what the pipe looks like. It's just a pipe.
This is one nostril?
And this is one side, yeah. This is one of the. We've got two of these. And so now what I'm going to do is just to sort of compare things, is I'm going to show you a cut from back here. So this is where it looks a bit complicated. And I'm going to show you both nostrils. So you see there's the left chamber and the right chamber. Flow's going inwards. And now, just for fun, let's compare this to the similar shape. This is from a single nostril. This is two nostrils. This is a single nostril from various animals.
Can I just ask a minute, where's the bone and where's the cavity?
The cavity is the dark. So the dark in all of these pictures is where the air is.
Really?
Yeah. So the air is going through a very thin slit. So it's really it's a very thin slit, right, which has this very complicated thing. And actually, this is a picture from Linda Buck showing, this is a sketch showing in mouse, because she did this in mouse to measure, this was in 1994 or whatever, showing the distribution of odoreceptors. And these are different types of odoreceptors. And this is showing you that the receptors are really covering, right, that the whole thing is covered with sensors. So now, you have to think about this from the point of view of an engineer or a fluid mechanician or whatever we're supposed to be at this place, which is that, I mean, you're breathing it in. So the physics is pretty simple, actually. You're breathing in, and on one hand, and on the other hand, you really want to absorb stuff. You're breathing in a scale. You're breathing in both the odors, but you're also breathing in, importantly, humidity, right? Humidity is very important, and you're also breathing in heat as you. And because your body is, because with the air you breathe in through your nose has to end up in your lungs, and so presumably you like to heat it before it goes in. So those are the things you're breathing in, and having a lot of surface area seems good for this purpose, right? Okay, that's all? Okay, good. Okay, so there are two competing issues. I just said this. This is basic.
Sorry, were they to scale, the drawings, or?
The drawings, there's a scale bar on the drawings, which is 5 millimeters. And this is 5 millimeters.
I was just wondering if the surface for the dog is much bigger than.
Yeah, it is much bigger than for the humans. So maybe that, but anyway, I mean, this is all nonsense. But anyway, it is bigger.
Are we to think of receptors as completely lining all those dark areas?
Yeah, that's right. So this is a sketch from the experimental paper, the original paper that showed the distribution of receptors. And, there are different receptors. I mean, so remember, I told you it's more complicated than this. There are, whatever, roughly 300 different receptors in humans. There are slightly more than that. If my memory serves, it's a factor of 2 more in dogs. Right?
Only 2
different-
more?
Hmm?
Gosh, only 2 more in dogs.
Yeah, well, I mean, we don't know.
600.
600, something like that. It's some number like that. It's bigger. It's a bigger of order factor of 2. I don't remember the exact number, but in humans, it's 250 to 300, the number of receptors, and they coat in a non-uniform way this shape. So, fluid mechanics. This is a fluid mechanics meeting. Okay, so there are sort of 2 competing design issues. I've already said this. One is there's fluid resistance. I mean, ideally, right, the entire thing would be surface. I mean, given, right, but on the other hand, then it would be too hard to breathe. And the other is basically scalar uptake. So if C is some sort of a passive scalar, then there's the question of scalar uptake. Now the question, the sort of, in order to analyze this, as you all know, right, you sort of have to know what regime you're in. And that actually, surprisingly, has been a source of some confusion in the literature. And in particular, and I don't, as when we started working on this, my colleague Dan Lieberman, who is wonderful, insisted to us that the flow in the nose was turbulent. The argument seemed to be that, anyway, so.
Is it steady state?
Well, you know how it is, you're breathing, so I mean, there's some frequency, right? So it's actually not steady state. Oh, I see, you said I wrote, so right, we have to analyze whether or not that's okay too. You're absolutely right. So in fact, there are more terms and we have to think about whether that's okay. So the first question, in fact, in order to do what I'm about to say, the main technical challenge was to come up with a reasonable argument for what regime you're in. As soon as you know what regime you're in, then you're done, basically, at least if you have read Darcy Thompson. But that was the thing. And so it turns out, actually, and this is really, so David found this, is that there are these amazing papers that people have written in which they've taken the shape of the nasal cavity from various organisms, done CT scans or micro CT scans of the whole, and then measured the statistical properties of them for us. And so this is an example of a paper, respiratory and olfactory terminal size. And within the nasal cavity of mammals is a complex scaffold of paper-thin bones that function in respiration and olfaction. And in this paper, they basically try to measure the surface area of this as a function of the properties of the animal. And so they produce these really wonderful allometric laws. This is very much in the spirit of Darcy Thompson, except that this is, sort of terminal surface area as a function of the volume of the nose in, various animals and mass and things like this. And the point is, if you sort of comb through the literature, and this is pretty recent, I mean, it requires CT scans and a lot of work to be able to do this, then you can find. Yeah.
Since this is in log terms, I can't quite see what the slope is. Is the saying that the surface area is going directly like the volume, or?
Well, I'll show you the exponents on the next slide. But they're all. But the point is now you have all the exponents. This is my point. Okay. So here I'll show you. We can stare at the exponents. So there are all these. If you just sort of go through the literature, there were 2 papers actually. One of which was that, and another of the other, where basically you could extract essentially the a la Darcy whoever allometric scaling laws for various quantities with the exponent as it depends on mass. And this is a table of the numbers. And so, for example, the skull length as a function of mass. I mean, that's actually, but you were asking, let's see, the surface area. This is the surface area of that dark region. It's 19 centimeters squared times mass to the 3/4 power. I mean, it's not really 3/4. I mean, this is just a, and so, but basically with these, the point of this is you could think about, the tidal volume is the volume of air that you actually breathe in a breath. Well, which is relevant because, remember, we're going to need to do physics on this, so we need to know the flow rate, right? We need to know the flow rate. And so the flow rate is the tidal volume times the respiratory rate, right? Because that's the flux of that you're sort of pulling through.
And these numbers for human, why that's so small?
These numbers are actually for many animals, allometric, it's a function of mass. So it's mass over kilograms to the B, so I don't know how many kilograms humans were like 50, 60 kilograms, something like this. So it's, the numbers become quite reasonable. I mean, 7, so 60 to the 1/3. So anyway, I'm going slowly because there's not much to say after this. So once you know this, you can then do this. So you can, for example, evaluate the Reynolds number. And so of course, to evaluate the Reynolds number, you need the velocity through the cavity. So L is the length, V is the volume of the nasal cavity, Q is the flux, which was gotten from what I showed you before. And it turns out that the velocity is 0.3 meters a second times the mass in kilograms to 0.15 powers. And anyway, when you put this, and you sort of can compute the Reynolds number, which is, it turns out 70 times the mass to the third, basically. And if you then ask how big, so okay, so now the question is it turbulence or not? So these are thin thingies, and the Reynolds number for turbulence is something like 1,000, I don't know. But, so if you set this equal to 1,000 and ask how big the mass has to be, it's like 2,000 kilograms or something like this. So it's totally ridiculous. So the flow is laminar in the nose. Okay, so, and then of course you can write down other quantities. So this is a quantity which actually I first learned of in hydrology. It's an interesting quantity. It's called the hydraulic radius. Right? I mean, and the question is how do you, given measurements of the volume and the surface area, actually figure out what the gap thickness is statistically? And what you're supposed to do is basically take twice the volume over the surface area. This formula actually has the very nice property that if you put in a circle, then you if you just imagine that you're doing it, in 2D. So if you do twice the area over the perimeter, then for a circle, it's 2 pi r squared over 2 pi r, so you get r. And then also if you take a rectangle, which is long and thin, right, then you also get the height of the rectangle with this formula. So it's a really very nice formula. Anyway, this gives you essentially the gap thickness as a function of weight. And you then actually, the other thing you can do is you can, this gets to the question of whether it's steady, is you can evaluate, so physically, right, there are various issues here. We have a pipe, and this is really very simple. There's an entrance length. I'm going to ignore the entrance length. You can yell at me about it if you'd like. There's the oscillatory boundary layer length, which is the square root of nu over the frequency, and then there's the ratio of that length to the radius of the tube. And this number, which I guess people call the Wormsley number, it's the ratio of the radius of the tube divided by this oscillatory boundary layer length. This is given by this formula according to the allometric laws. And this actually is interestingly, right on the edge. So this is about 1 actually. I mean, you can see it's 0.7 times something to the 0.9. It's about 1, essentially independent of mass, which means that there is actually that is, if you were to think about the resistance, for example, to flow in this thing, the oscillatory boundary layer does contribute. Actually, we did lots of simulations. We got very worried about this, and so we started just making these things and considering this is the resistance. This is the resistance divided by the resistance when the Wormsley number is 0. This is how much amplification there is as a function of the Wormsley number. So around 1 or so, where we are, there's about a 50% increase in the resistance. Anyway. Okay.
These are heuristic, completely heuristic.
Which heuristic?
These allometric laws.
Well, they're from data.
Yeah, that's what I mean.
I mean, I don't know if they're not heuristic. Heuristic means you make it up.
No, heuristic means based on experiment, without any theory.
Empirical.
No, that's empirical. Empirical is, heuristic means you made it up. Heuristic is like this talk. I mean, these people worked hard to get this data. Okay, so, sorry, this isn't, anyway. So now you see, now it's laminar, phew. So you can actually calculate. So anyway, making all of the suitable, approximations, which actually we were pretty careful to test, I should say. This might sound heuristic, and in many ways this talk is heuristic, but we did actually try to be careful. So what you have to do, right, if you want to actually compute the flow through one of these things, is you that you have to. I mean, assuming that the channel is slowly varying axial direction, Laplacian perpendicular is in the plane, right? And P over L is the pressure gradient. So you basically have to solve this with, of course, U equals 0 on the boundaries. And when you do that, then you can compute the flux. Once you've done this, you can compute the flux through a channel, which is given by this formula. And you then can compute the ratio of the pressure to the flux to get the resistance. And if you non-dimensionalize, the resistance actually is given by a dimensional component. This is viscosity times the length divided by the area squared. And then there's a dimensionless number which only depends on the detailed shape of the tube, right? Which is in this. So remember, what we're talking about here is tube shape, right? This is getting back to it. So the shape is contained within that number. And then you can do the same thing for scalar uptake. So in this case, the Peckley number is high, so you can neglect axial diffusion. The way we do this calculation, because we have to actually to measure the efficiency of the scalar deposition, is we solve this with a boundary condition that C, the concentration, is equal to some number at the walls. That number, if it's olfaction, should probably be 0. You would really like to suck up all of the volatile compounds. If it's heat, then you might be heating the walls up to some constant number. We then solve this by simply factorizing it into a component which depends on Z and a component which is in plane. And you then basically can turn this into an eigenvalue problem for the decay rate of the scalar through the tube. So basically the C of Z, the Z dependence as you go inwards, the concentration is decaying exponentially because it's being uptaken by the walls, of course. And so you end up with an eigenvalue problem for lambda, which depends on C tilde. U, of course, is given from the previous solution. And then what we do is we measure what we call the scalar exchange efficiency, in which what we basically say is look, there's the initial input concentration, there's the C at the boundary. So if we were, for example, considering a volatile, CB would be 0, and C of 0 is just the input concentration of the volatile when you go in. C of L is the concentration when you go out at the end of the nose. And this is basically a measure of how efficiently you've taken this up. I mean, this is essentially, given that C of Z is decaying exponentially, this is essentially the length of the tube divided by the smallest eigenvalue of this operator. Now notice, this of course also depends on the shape. So sorry, this is all, the shape is hidden within this for any shape tube. You can solve this, and if you sort of work this out, then there's what we call the scalar exchange efficiency. This is essentially a dimensionless number that only depends on the shape of the tube that basically is measuring the efficiency of exchange. So now the basic game is we have two quantities. We have fluid resistance, we have scalar uptake. They are each measured, quantified by a dimensionless number, which depends only on the shape of the tube. And the question is please now choose, as you put your engineer hat on, please now choose the shape of the tube. So the way that we do this is we basically ask for, and this was our choice, for a given exchange efficiency, that is, given that you've decided you're going to uptake volatiles or heat at a particular level of efficiency, then please find the shape with minimal resistance. That's the problem. That's the Darcy-Thompson that we solved. I don't know. I'm not very impressed. And then, so what I'm about to show you is plots. So this actually is so I'm going to plot the ratio of the resistance to the exchange efficiency against the exchange efficiency. So what we're going to be doing is asking what is the minimal resistance for a given exchange efficiency. So actually,
Can I ask a stupid question? Can you have, for any value of the exchange efficiency, do you have a candidate that you can start with if you want to do this numerically, for example?
Right.
Do we know what, are they all attainable? Is there?
Good. Can I show you the next slide? I think the answer to that is no, but I'll show you what we did. So I mean, in the absence of insight, do simulations. Sorry. So what we did was because we didn't really know what to do, and as you know, these things are actually hard. Like if you actually really want to compute the optimum of what I just said, I mean, you can do it. Do you remember Henry?
Yes.
Yeah. Henry worked on such a problem. It was really painful, right? It's really actually hard to write down optima because these are functionals of the shape, and it's really a mess. And so we just wanted to know the answer because I'd gotten tired in old age or something. So basically, So these are filling in the plot for various shapes. That's what this is. It's just so that you can look at what happens. So for example, if you take a circle, here is a circle, right? And these are sort of dimensionless numbers, right? And then if you then elongate it into an ellipse, then basically this is what happens. The rectangular duct behaves differently. There are these things that I must admit I don't understand. That is, I don't understand why an elliptical duct isn't like a rectangular duct, because the only difference is the corners. It doesn't make any sense to me, and but this is apparently the case, right? Of course, the elliptical duct is not an elliptical duct with just rounded corners. That's not what an elliptical duct is. An elliptical duct changes slowly. I would love analytical insight into this. We tried and basically failed at such things. These are multiple pipes that are basically placed in parallel. This is parallel plates, and this is actually this is a rectangular duct, and this is a rounded rectangular duct. So a rectangular duct where you just put a circle, a circular cap on the two ends. And what you see is that if the game is for a given exchange efficiency, pick your number, you would like to find the shape with minimum resistance, the answer is parallel plates. Now, this is not a search over all shapes, this is what we did, but this is.
We're talking about curved pipes which can have secondary flows. That
Right,
can
we're gonna
affect
talk
these.
about, right, good. So, at the moment, we're not talking about curved pipes.
These are all straight, are they?
Well, okay, so let me be, but you're right, there are curved, so we're gonna talk about curved. There's a slide at the end of this which is called worrying. And one of the worries is that.
Okay, so you mentioned this are numerical results. I'm not a food person, but I mean, intuitively, does this make sense? Like for a rectangular duct with rounded rectangular duct, right? Shouldn't the results for that be between the rectangular duct and the elliptical duct?
Well, I mean, this was, as you might imagine, the subject of much discussion. And
Are you going to discuss that?
I don't really have anything to say. There are these old papers with exact formulas for some of these. This isn't only, I mean, these were our numerical results, right? But there are old papers that we calibrated this against with exact formulas, for example, for elliptical ducts, and our numbers are correct. On the other hand, I don't, I'm really sorry. It's a bit embarrassing. I mean, fortunately, the answer ended up being the parallel plates, which is
So in the pictures you showed us from the experiments, there's other wiggles. What happens if you take a shape and you wiggle it? You add some wiggles. You can do this numerically, I guess.
yeah, you could do
Like
that.
a wiggle.
Yeah, you could.
rectangle or-
You could do that. You could wiggle it and show that the wiggling made it worse. Is that what you
Yes,
mean?
yes.
Yeah, you could do that, and we didn't do that, but we could do that. The problem with this, right, this is not a theorem that this is the optimum. If this is good, and I mean, as you know, I mean, maybe Eric, you remember with poor Henry. Poor Henry, we were interested in the shape of the nozzle, which for fixed pressure produced the smallest droplets. Think about that one. So it's a shape with constant mean curvature, where you basically pretend that the bifurcation point is at fixed pressure, the pressure is the same, and then you're allowed to change the shape of the nozzle. And we solved that analytically. If I showed you the analytical solution, you would all be very impressed with all the equations. But in the end, we learned nothing more than this.
But Michael, given these results and that they are very surprising, because I agree that the rounded rectangular duct should be between elliptical.
Well, I don't know why you say that. I mean, the elliptical duct does have a different shape. I mean, let's be very careful. I mean, I understand your point. I mean, sorry, I've made this,
But can
I've
I-
said what you've said too. Well, let me just basically make sure you understand. I want to make sure you understand. An elliptical duct is like that. The whole thing is curved, whereas a rounded rectangular duct, right? There's a. You see, different.
But the point I was going to make, couldn't you have some parameter and deform the shape and have a series of curves that connect smoothly between whatever, rounded, rectangular, elliptical, and then you would have seen what happened.
Yeah, you could do that. No, it's a good idea. We didn't do that. I mean, see, the thing is that we wanted the shape with minimum resistance for a given exchange efficiency, and that was clearly the parallel plates. It's not a proof, it's just a statement. Okay, so, is anybody else? I mean, I think this is an interesting problem. So,
What are you keeping fixed across all these geometries? How do you compare? Is
Oh, we're keeping the
Cross-sectional
area,
area.
we're keeping areas fixed. So this is only the prefactor. So we've subtracted out the length. So remember, we've extracted the dimensional part. So this is the dimensionless part. So it's fixed area.
How do you compare infinite plates with an ellipse?
Oh, good. So the plate, good, thank you very much. Okay, because a plate is, how do you forget that? So what we do, and this is cheating, I'm not sure if it's cheating actually, I think it's not cheating, this is what we do, is we imagine that the plate is periodic, and we then solve the eigenvalue problem. So we have to actually solve an eigenvalue problem, assuming, right, a particular periodicity, and the area is then the length times this length, times the gap. So then the area is fixed. So then you can compare that area, and then this is sort of well-defined solution, you could compare that area to the rounded rectangular duct.
So you don't have non-slip boundary conditions.
No, well, we
On the
do,
periodic
actually,
bank.
no, we do, we have,
On the periodic
but
bank.
not on the periodic, no, we don't actually on the periodic thing. But the point is that you look, the rounded rectangular duct does approach it, though, as it gets long enough.
Yeah.
Right, so, and I mean, this is really why, so what I'm about to do is to simply write down the formula for the rest of this talk, which fortunately is going slowly. The rest of this talk is I'm gonna just take this formula from parallel plates, which we now have, I'm going to simply tell you what the gap thickness is supposed to be, and I'm then gonna compare it to the experiments. That's essentially the rest of the talk. I can stop now, actually, and it works, right? I mean, you know how this is like a Darcy-Thompson-like thing, these things always work, right? That was sarcasm. But it is true that asymptotically the rounded rectangular duct approaches the parallel plate, which is the justification for doing that. And the nice thing about this is that you can sort of write down analytically what the answer, I mean, up to a number, which is the eigenvalue you can write down. No, that's good.
Can I ask another question?
Please.
So what I don't understand is I thought the pipe of a circular cross-section was, among all the pipes, the one with the least resistance?
But this is for a given exchange efficiency. So remember, I'm not plotting resistance, I'm plotting resistance over exchange efficiency. I've cheated a bit, right? Because remember, exchange efficiency is that I want, right?
Right, but it says that if I take a vertical slice, then I'm comparing only hydraulic resistance. If I take a vertical line, then I fixed the
I think the
exchange efficiency.
That's right.
Right, but that means that I have something that's better than a circle.
If I fix the exchange efficiency, but the point is that parallel plates, right, for, if I.
No, I meant the purple line. I'm just worried about, I don't understand the
Which one?
purple, why there's something underneath.
This purple one?
Yeah, just underneath the circle, there's something better than the circle.
Oh, this is an
Right.
annulus.
Parallel plate.
Oh, no, sorry, I'm missing, this is rounded duct.
This is a rounded
This is
rectangular
parallel
duct.
plates. No, I'm actually confused about that.
Or maybe we can talk after. I just thought that if you fix the exchange efficiency, nothing could be better than the circle.
No, because I guess I'm confused. The circle has the exchange efficiency that it has. And so I'm allowed to basically say I'd like a better exchange efficiency. And then the answer is not going to be a circle. Right? I mean, the circle, right, the exchange efficiency of the circle, if I code it with absorbers and I ask, I put in a passive die and I say how much, what is the exponential decay by the end? It is what it is. So, okay, that's what you get for the circle. Now, Eric, I want better than that. So you can make it better than that, but you have to squash it because you actually have to make it so that that there's a higher probability that the molecules will randomly walk or whatever into the boundary, and but then that's going to increase your resistance. You see what I mean? So I agree. If there were no constraint on the exchange efficiency, then it should be a circle. But the point is that for this, that's the engineering challenge. Okay, so anyway, then, sorry, this is sort of dumb. For parallel plates, there's a formula. So A is, again, following Rich's comment, it's L times the periodicity length. So this is really, right, the periodicity length over the gap thickness, which is what you would expect for an eigenvalue. And then there's some prefactor that you can compute. And basically then, but what we do is you take this formula, plug it in here, and what we want is for given exchange efficiency, what is the gap thickness L? And you can write it in this nice suggestive way, where tau is a time, right? It's L, the length, times the area over Q, right? And so this is the square root of d tau, so the formula with a prefactor. And so now what we would like to do is test this formula using the allometric data that we have, because the allometric data. And so for that, what we're going to do is take the surface area of the nasal cavity, and it's a function of all of these parameters. And there are various scaling laws that come in that follow from this that are sort of non-trivial, which you should just, this is just sort of algebra and formulas, but this, And so then we tested it, and I wanna, just wanna show you, so this is our plot. So this is the surface area of the nasal cavity as a function of body mass, and this is the data. This is human, which is off this line. This line is the parallel plates. Now, the problem with the parallel plate solution is that when the body mass gets very small, then if you maintain the parallel plate solution, then the efficiency doesn't remain, the epsilon doesn't remain constant. This is sort of roughly one of the things that you were all yelling at me about a little while ago. This is CK over epsilon, so it's flat there. But the resistance actually, right, is when the thing gets smaller, the boundary effects start to matter. And so what we did was to take a rectangular duct and to basically ask for the rectangular duct. We set the exchange efficiency equal to 1. That's just a number. That basically means that, like, whatever, 60% or something of the stuff is absorbed by the time you go through the channel. And this line corresponds to the family of rectangular ducts which have exchange efficiency of 1 as a function of body mass. And, it works quite well, except that humans are off the line. Now, Dan, my colleague, we'd all like to think humans are special. I don't know if humans are special. But what we did do, though, because that's too complicated for me, is that it turns out that there's this, so there's this standard nasal cavity that I showed you before that was gotten as an average. So we took the nasal cavity and we calculated from it, going as a function of distance from the input to the output, what the hydraulic resistance, what the hydraulic radius is, that is what the gap thickness actually is as a function of distance, because we had this, so we actually could do it point-wise. And this is a plot of the hydraulic radius as a function of distance along the nasal cavity in the humans. This is the area as a function of distance in humans from the standardized nasal cavity. And what you do see, notice these axes have very different scales. This is a couple millimeters, this is centimeters, this is 10 centimeters or something like this. And this is the prediction, this is what our formula would have said. And the standardized nose does go below. It is pretty constant actually over the whole thing. That part is supposed to be a victory. But then there's a gap, there's about 50%, humans, it's about 50% below what it should be. So, okay, so that's basically, I have more to say because you never stop talking, but that's basically all I have to say. There's this sort of worrying slide. So, we did the worrying as best we can. This is, what is the word? This is the best we could think of doing. So what we did was we basically did simulations of bending and branching, actually. So bending, we bent it, so we bent the thing and we measured, how much these numbers, their exchange efficiency and the resistance change when you start to bend the thing, and at least up to sort of it changed, but not a whole lot. And then we also put in branches. We put in T-junctions, and we started simulating how these numbers changes with T-junctions. And it's clear that these things have an effect, but it's on the order of 10% effect for the numbers.
What Reynolds numbers are we at just now?
The Reynolds numbers, if we go back, so I was doing this over body mass. So so the Reynolds number is less than 1,000 because it's not turbulent, but it's depending on the body mass. So this was an argument over a range of body masses. So this is that's H. Sorry, Reynolds number 70 times. So for 1 kilogram, then you're at 70, and for 4 cubed kilogram, you're at 280. So I also, like you, am not unworried about eddies when the thing bends, but and this is not a good argument, but this is all I have, which is that for the amounts of bending that we were estimating that were in the nose, and we just sort of simulated, and it didn't make a huge effect on these numbers.
Okay, so you tested in that range.
Yeah, in that range, we just tested different. We just did simulations and measured them numerically and checked how far off they were. Because clearly, if they were way off, then this whole thing goes out the window. As you pointed out right before, so that, like, if you bent it and the resistance went up by a factor of 10, then throw this in the garbage can. But that's not what happened. These were at most 10% effects. So, I know it's not very satisfying. At least I don't feel very satisfied right now. But in my defense, it's the nose. Okay. Does anybody have anything? I'm gonna just quickly tell you two other things we did with this, and then I'm gonna stop because we're out of time. I don't wanna go over. The worst sin is to go over. So actually, one of the things we've been doing recently, and this is sort of modestly useful, I guess. So Robin is a nasal surgery, a nasal surgeon at Mass Eye and Ear, and we got interested. So she got us interested in basically the fact that there really is no good way to measure flow in the nose. So, so in fact, she was showing us this device that they use to measure flow. Like if you go in with nasal obstruction, there's this big thing they put over here, and then you breathe into it, and they measure the volume of this. It's sort of unbelievable. And so, anyway, we befriended this very excellent computational fluid mechanician named Simona. And Simona basically has the following remarkable ability. If you give him a CT scan, then he produces a lattice Boltzmann simulation. So that's very useful and so what we've been doing with, really David has been driving this again, and with Simona and under Robin's direction so they have these scores they call nose scores, right? When your nose score is low, then it stands for something, IT nasal obstruction. Right, but as you, but you know, there's sort of these, like, it's from breathing into this container, right? And they, and they're just sort of empirical numbers. And what we've been trying to do is to basically set up a study. We've set up a study in which Robin, you know, a patient comes in, Robin sends them to surgery, but before she sends them to surgery, she takes a CT scan of the nose, and then she measures the nose score, and then she does surgery, and then she takes a CT scan of the nose afterwards, and then we just calculate the fluid mechanics and try to see if we can see things. And it's sort of, we've been doing this a bit. Actually, this is Simona. So from CT scan to three-dimensional reconstruction, and then from three-dimensional reconstruction, he puts in a lattice Boltzmann mesh, and he basically solves for the flow. And this is just an example of a movie from Simona. If I can make this work. I can't. Oh, there's one. See. Breathing. But anyway, I'm going to just show you two slides of this.
How does he force the flow?
With some respiratory pressure. You have to force it with some reasonable pressure. I mean, that's part of, there are lots of details in this of how to do this, but basically, this is an example of a plot. This was our first attempt. So these two people had noses so this is nose scores as a function of resistance from the simulation. Because what you'd like to say is that resistance is a physical thing that has to do with nasal obstruction. So these two people have collapsible noses. They have some defect so that their actual nose collapses when they breathe in, which you have to ignore them. But you know, we sort of, this is the first shot, and this is, this is not, it's not terrible, right? I think it is terrible. And this is a plot of the viscous dissipation. So this is a plot of the viscous dissipation. I mean, this is the problem with trying to do something that's actually useful as opposed to normal, right? It's hard. So okay, so here's one more. Maybe this is a slightly better victory. So this is the first patient that Robin subjected this analysis to. So this is the pre and post-op CT scan. So we computed the velocity and, more to the point, the viscous dissipation. So viscous dissipation is telling you where the nose is blocked, and indeed, according to the calculations, the viscous dissipation was high at a particular point in the nose, which was sensible, and after surgery, the patient felt better and the problem was relieved. One data. Okay, so anyway, we're right now we're in the process of putting together an actual thing, doing statistics on this. I suspect actually by the end, this is gonna, you know, if I ever came back here and talked about this, I suspect that the plot at the end will look something like this as well, but you know, maybe it'll be useful. Okay, so finally, the other thing that we spent some amount of time on, which I think I'm not going to talk about right now, is the sort of information theoretic part, not fluid mechanics, of the odor receptors, because there is this sort of this is not changing the topic. Get rid of Darcy Thompson, you know, et cetera. So I mean, it's sort of an amazing thing. I mean, there are 250 odd odor receptors, and you have to identify on 2,000 molecules, and it's even more complicated than that. The aspect that we got interested in is, you know, again, if you're cooking, when the odors come up, it's not like there's a single molecule that's coming up. It's actually pretty complicated. It's some mixture of molecules, and we're very good at distinguishing different mixtures. So what the nose is actually being given with. It's not like, I mean, if it were just as simple as 250 250 things and you have a molecule, and of course, several of them will light up. I mean, in principle, whether or not a receptor fires or not, right, each receptor either binds or doesn't bind to every molecule, so there are 250 receptors, but that means there are 2 to 250 different outputs in principle. I mean, of course, many of them are going to be dependent, so it's going to be a much smaller number than that. It's not that many because there are going to be correlations between, but you still are going to have many more than 250 different outputs. So it's actually not totally crazy that you would be able to identify 2,000 molecules with this. But the problem is that in the natural environment, you're presented with many different molecules, and if your only signal output is that, oh, these lit up, you don't know which molecule it came from, actually. So it's not like, it's much more complicated than just a single molecule binding to a single thing. So anyway, we worked on this for a while, and we just did some calculations, which suggested some experiments, but anyway, I get rid of this. I'll leave that, and instead I'm gonna just end by showing you David. So this was really David's work. Hopefully I did it justice. Thank you for listening to me.
I know some of you have to leave at exactly 12, so feel free to fly away if you have to. Questions? We have time for some more questions. Yes.
So there are people who are able to actually run a Navier-Stokes simulation with a CT scan. Did you try to do that as well?
Yeah, that was the last part with Simona.
That was Linus
Simona.
Boltzmann, that was not Navier-Stokes.
Say again, that was Linus Boltzmann.
That was Linus Boltzmann, right? That
Yeah.
was not Navier-Stokes, right?
Well, Linus Boltzmann is an approximation to Navier-Stokes. How do you, I mean, that sounds really hard, actually, to do that. But if there are people who can do that, no, we haven't tried.
Oh, this is I mean, I know people doing porous media who do that.
But without Linus Boltzmann, seriously?
Yeah, sure.
They discretize the mesh, they make a mesh, and they solve it on.
Hmm?
Yeah, finite elements.
Yeah.
have-
Yeah,
With finite
that's-
elements
that's
on
what it's-
a thing of
that's
this
easy, yeah.
complexity from a CT scan? Really? Wow, I didn't know you could do that. You don't like Linus Boltzmann? No, I'm asking, you don't like Linus Boltzmann?
Not too much.
But why is it?
It would be a long discussion, I'm afraid.
But I know, I'm just curious.
Inappropriate for this.
You're being recorded too, actually, we're all in this
But
together.
not his image,
Not your image.
just sound.
Voice recognition's gotten much better though.
Question.
Your calculation of the fluid mechanics is sort of like based on Poisson flow, based on it sort of being laminar and
Yeah.
reasonably large Reynolds numbers, but not turbulent.
Yeah.
For the take-up efficiency, you're also assuming that your chemical entry length is short
Yeah.
compared to.
Yeah.
Is that
No, okay.
consistent?
Yeah.
Because your
Right.
fluids was just
No,
above
because
on
D
the
over
edge
nu is
and
one. No, I hear you.
chemicals-
Right, because D and nu are comparable, right? This is your, so therefore, right, the entry line to the flow. That's what you're arguing.
Yeah.
Yeah, so we also did, as part of the worrying, we also did simulations with, including entrance effects. And it also didn't have a huge effect on this. It is true that given, that nu and D are not so different from each other, that you would worry that, we worried about this. So we did simulations and, I mean, it didn't make a huge effect. I mean, in the end, apparently you end up with plates, right?
So maybe is the resistance in the nose, so that it's small, is really important because when people like exercise or doing, they can open the mouth
Oh, well, but
to breathe in. Like if you look any athletes or runners, like,
I
or even
think-
maybe animals.
yeah, but I think animals actually, there are animals that only breathe through the nose. But also, yeah, with respect to us, I agree you could open your mouth.
Some animals breathe it without nose.
Yeah, I mean, no, this is the problem, if I might say, I mean, despite this talk about calculating an optimum and comparing it to experiments, I mean, this is the problem with talks like this, right? I mean, the problem with talks like this is that it worked pretty well following our nose. I mean, we did try to be careful with respect to these various aspects of the fluid mechanics, but it's sufficiently complicated that it's sort of even hard to be careful. But in the end, whenever you go to a talk, which is called optimum, like this, then you knew what the last slide was going to be. That's my problem with talks like this, because of course I wouldn't be giving it if I didn't have the plow with power law with the line through it. But yet, there could be something else going on. So I view this as a form of hypothesis testing, right? You're free to come up, I think that may be the right way to view this. This is not a statement, this is a hypothesis, and I've presented evidence in favor of the hypothesis, which is up to you to get rid of the resistance thing and to try to think about it from a different perspective that would be intellectually consistent. So this is at least, I would argue, a self-consistent picture, but that does not mean that this is true. I think that that's a fair statement, not only about this talk, but about many talks, including those of Darcy Thompson, where he's still alive.
On the receptors issue as such, and combinatorics and whatnot, there was an intriguing suggestion made some time ago, I think maybe 20 years, that actually it's not just a question of biomolecular template fitting like an immunoglobulin, but also some element of infrared spectroscopy. This guy says his name was Luca Turin, I think, the guy who was talking about this. Is that considered to have any traction these days?
I don't understand how the spectroscopy would work.
Well, I mean, he was arguing from the kinds of molecules that got detected and the kinds of molecules that smell similar and that kind of thing. And
Oh, you mean
he
he's
argued
arguing it's similar spectroscopic
the
signatures?
infrared vibration modes of those molecules may help to explain that, he argued. I don't know how good the evidence really is.
Well, I mean, but, okay, so that idea, I haven't seen it discussed with respect to spectroscopy, but the notion that the vibrational modes of the molecule
Yeah, that was it. That was it, yes.
could be important for the way that the receptor detects it. I mean, so there's the sort of lock and key thing where you think of but I mean, nobody really knows how this works. Whether the vibrational parts of the molecule are important for binding, that I don't know that anyone knows. I have seen that discussed in recent literature, but it's very hard to tell. Right? I mean, one of the things about these olfactory receptors is that as of now, maybe I'm 6 months out of date, but as of 6 months ago, the crystal structures weren't known. But even if the crystal structures were known, they're membrane receptors. So even if the crystal structures were known, then what would you do? I mean, you could get a crystal structure with a ligand in it, but then they've frozen the damn thing. So this is hard.
Okay, so it might be a dynamic lock and key rather than just a static one, for all anyone knows.
It might be a dynamic lock. And actually, the calculations that we did, which were information theoretic and thus subject to the same types of criticisms that I just described, because we were assuming something and then calculating something, sort of suggested binding energies that were reasonably consistent with experiments run the order of a KT, which is not type binding.
Eva?
So can you please again explain the motivation behind the optimization?
Which optimization?
So the optimization that you chose to define the problem?
This,
Yeah.
well, we just sort of followed our nose, through this, and it seemed like the problem was solved, and so we did, and then we compared it to experiments, and then it worked, and so then we declared that was the only possible solution.
I think you meant the ratio, the choice of the ratio.
Yes.
I think you meant the mathematical choice.
Oh, you mean the choice of, I see, you mean the choice of minimizing resistance for given exchange efficiency. So I would welcome other hypotheses for what you could have done. That's what the question is what is being held constant, right? I mean, this is looking across a wide range of organisms. So implicit in this was the notion that what was being held constant across organisms, because that's what I showed, right? I basically plotted across, I said everybody has the same exchange efficiency. Now, I don't know why. I mean, it's not an unreasonable thing to say that the exchange efficiency is what's constant. That is to say that when you're presented with a puff of air, right, the fraction of the odor molecules that we take out of it in our puff is sort of similar to that of a dog, is not unreasonable. On the other hand, it's not guaranteed to be true either, and you could have chosen something else to optimize. I mean, this is the way that we formulated.
So another related question is that I've read articles on just if you keep one human species and not look into other organisms. So depending on temperature and humidity, people have either bigger or smaller noses. There's some article that I've read. Is that something that can be explained using this?
We didn't try to, no, not to my knowledge. I mean, actually, at some point we spent some time, a couple of weeks trying to understand why there were two nostrils. Based on theory. I mean, because
vertebrate bilaterality, surely.
Yeah, well, that's one, but there's also the notion of directionality, right? This is actually more with the external problem than the internal problem. That is, to what extent can you, given a puff over there, can you tell your left from your right? And that was, we got confused about that too, because
well, the brain has bilaterally evolved differentially. Maybe the nose did as well. Maybe the left smells some things better than the right.
Really
Perhaps it's Yes, Jane and then Reski.
So most of the sensors have this logarithmic sensing. And within this model, is there some indication?
What do you mean by logarithmic sensing?
So, in other words, the response depends on the logarithm of the concentration. So,
That's just advection diffusion, isn't it? The diffusion brings in an exponential dependence. Isn't that why you have to
so I
take
wonder
the log?
if that can show up in this, so the log.
Yeah, no, I'm just thinking about what you're saying.
The fractional law.
Well, I mean, there is this exponential decay, which I think is just.
So that's why I'm saying, well, this is the absorption rate. So the
Right.
absorption, once you model that, that should indicate there'll be a logarithmic rate.
You're saying it's diffusion rate limited, isn't it? That's your model says anyway.
Right, so that would be actually hidden in this. If you're assuming already this is a diffusion limited absorption.
Right.
You know, sorry, I'm just looking at you confused because there's also, of course, the concentration difference of the detector. There's another part. of this,
Concentration
dependence of the
different.
detector. The dependence of the detector. Because remember, the detector is a receptor that binds or doesn't bind to this molecule, which is dissolved in a solution that is around it. And as you change the concentration, that's actually quite sensitive to concentration as well, because the
That's an
probability.
individual receptor versus this continuum modeling, which is essentially
sure.
what you have is. So that D perpendicular that you have is, and that's, where does that come from?
D perpendicular.
I guess in your case, so you have this equation for the C diffusing to the nose.
Yeah.
And so you mod that by diffusion process, which has this coefficient, diffusion coefficient, so that in part can come from individual receptor, which is a function of C, versus.
No, the diffusion constant is just the diffusion constant of the odor in air. It's just a physical constant.
Odor in air, no, but the absorption rate.
Well, the absorption is just on the boundary, it's just the boundary condition that you're applying, and
I
it's just
know, in your
all sucked
model
into the
is,
boundary condition.
in your model is the boundary condition, and which you construct. You say here's a boundary condition which behaves like a diffusion with such a constant diffusion coefficient. If you look at the receptors themselves, in order to model their absorption, and then the next part that you're talking about comes in, which is the receptor themselves. So in other words, that your D can be a function of C.
D is the diffusion constant, sorry.
Right.
No, I don't agree with that at all, sorry, I don't understand. D is the random walks of the odor molecules in air. If what you're saying is, I mean, I agree with the following. If what you're saying is, wait, I'm just trying, that the fluid mechanics problem I just described, the solution to, assume that the concentration was zero on the boundaries, which basically assumes extremely efficient uptake. So one could imagine sort of modifying the dynamics of the receptor uptake so that it were more complicated. For example, it had a time scale in it or something, or it actually could have an uptake which itself was concentration dependent. One could actually model that being in, but if one did that, then that would have the effect of doing is changing the boundary conditions, right, on the fluid from being C equals 0 to something else.
So at the moment you have, what the boundary condition is C equal to 0.
At the moment, C equals 0, although there is also a worrying, on the worrying slide, actually, we also investigated changing the boundary condition, right, to make it essentially a mixed boundary condition, which is C plus some proportional to the gradient, right, which is, if you were to write down a model of a dynamical receptor, then that's what would happen. Now, we didn't make it concentration dependent, in fact, the prefactor in that, we didn't, but I don't think it would matter very much.
No, I think it would, because of what he was, yeah, anyway.
Okay, maybe time for one last amazing question, Areski.
I'm not sure it's amazing. So you mentioned the proteins that facilitate the dissolution of odor molecules.
Yeah.
They're also involved in recognition, or?
Well, that is an interesting question. So at some point, one of our failed research projects in this was that we were going to, because we were studying the information processing from the receptor, and we wanted to actually do it from the odor binding factors. Because there are many odor binding factors, actually, and you could imagine that different odor binding factors would facilitate the increased solubility of different factors, and thus it could be, a process in the thing. One clearly, I think we resigned from this idea because it's clear that one could make models that did whatever you wanted, depending on what parameters you chose, and given the absence of data, it seemed like a foolhardy exercise. But it is possible that that's important. I just don't know.
This, I propose we thank Michael once more.